Yes, you can hear. And I think it's recording. So Yan Li holds a bachelor degree in electrical engineering and a master's degree in the Department of Mathematics and a PhD degree from the Graduate Institute of Communication Engineering, all from National Taiwan University. From 2021 onwards, he has been affiliated with the Honghai Research Institute as a postdoctoral researcher. His research focuses on molecular communication, mathematical physics, information theory, and quantum information. Let us all welcome our speaker.
Hello. Good morning. I'm Yan Li. Today I'm going to introduce a recent work from our group, but this is not a quantum result. This is a result about classical communication, and more precisely, is a subfield of called molecular communications. So I will first introduce. Let me introduce the title first. This is a special kind of channel called first arrival position channels, and we have analysis the noise distribution, and then get some new capacity analysis result. And the authors include the four authors are listed here, and we have some collaborations with Georgia Tech University. So let me get started. So this is the archive number of the newest version of this paper, and maybe you can, someone who has some interest, you can check this out. Oh, this is the outline of today's talk. Because this is perhaps a new communication concept, so I will introduce first what is the molecular communication. Can you see the hand mark? Yes. Okay. And then the second item is I want to go briefly through the diffusion theory, very brief version of how to describe the diffusion phenomena in the fluid media. And next, I will introduce the main topic called the FAT and FAP channels, and then we go to the capacity bounds part. Okay, so our result is mainly focused on the FAP type channels. Before starting, this is some these are some good reference for maybe a beginner or someone who has interested in this field. You can I recommend the first reference for the beginners of this field. The first paper is a good review paper on this field for molecular communications, and for the FAT first arrival time channel, you can check these two good reference. The second reference is the first paper to raise the concept, to propose the concept called the FAT, and the third paper is the follow-up work. And the fourth and fifth work are the maybe a precision analog of the original time channels. Okay, so these are the 5 good reference to begin. And let me start with today's contents. Okay, the first part is to give a quick introduction of something called the neural networks and something called diffusive molecular communication. The big concept is the neural networks. It is all the concept begins. So the neural networks, you can see these things in nature because in the cells or in the bacteria, groups of bacteria, they always have their method to communicate between each other. Say 2 bacteria, they want to communicate. So because in the human's viewpoint, we always think of a communication system related to the EM wave systems. But obviously, bacteria don't use EM wave to communicate with each other. So people start to be curious about how the small systems commute in nature, not using the EM wave structure. So the question is, can we understand and further control the signaling in tiny systems? The first step is to understand, and then maybe we can build some man-made system to mimic these communication scenarios. Okay, so this is the famous saying from Richard Feynman, and there's plenty of room at the bottom. Although we can explain this sentence into a quantum understanding, there are also this saying also give us some ideas about maybe we can build some communication systems using tiny molecules at the scale, say 10 to the -9 meters roughly. So this is the conceptual picture about neural network, and some transmitter and some receivers, and the green balls are the molecules that carries information. Okay, so take this out, or maybe this. Okay, thank you. Okay, so let me continue. So molecular communication, let's abbreviate it as MC. It can be viewed as an approach to realize this kind of neural networks, and it has the properties listed below. So the first property is feasibility, and then appropriate size, biocompatibility, and energy efficiency. These are all very rough ideas, so I won't go into the details. We can understand just the MCs and approach to realize this neural network concept. And for the next page is some challenges for these diffusive MC systems compared to the traditional EM wave systems. I list four main challenges. The first one is the most important one, is the stochastical property intrinsically embedded in these systems, because the molecules will diffuse following, say, Brownian motion, and Brownian motion is totally random trajectory. So it is hard to predict compared to the like EM wave systems. And the second property is the delay and the range. The third is the range, because molecular won't go as far as the EM wave goes. So the range is a problem, and the delay is also a problem, because EM wave travels in the speed of light, but molecules diffuse in a very slow speed compared to the EM wave. And the final thing I will bring up is the fragility, because because Brownian motion is kind of very random, so we are hard to control these motions. Okay, so let me go to the next slide. This is the conceptual picture. This is a transmitter and a receiver. All the communication systems can be depicted as this picture, and the difference is we now use information molecule to convey our information rather than using the wave, the EM wave. So this is a simple model. And let me show a very simple 4 pages to let you know how this works. In a fluid media, we can think of a transmitter and a receiver are put in a fluid media, and these red balls are the inversion particles. And if the red balls just follows the diffusion equation, they will gradually approach the receiver and then captured by the receiver. And we are thinking of whether we can design some of the receiving device that can decode or decode the message from the red ball. that is transmitted by the transmitter end. Okay, this is the concept picture, and this is the real system. In 2014, roughly, the group, the Professor Eckford's group, and they built up a tabletop molecular communication systems, and just a very simple system. This is like alcohol molecules and a fan to boost them to the receiving device, and the message is successfully decoded. So they have a paper about these tabletop systems, and I listed the paper here. Okay. Okay, so the final things for the first section is the 6G communication. Okay.
Because you said that they do the experiment.
Yeah.
And like using like the
alcohol
the
molecules
there.
Yeah.
Which takes some alcohol droplets, right?
Yeah, alcohol.
But you said that the message was transmitted. Is there any message? What is the message?
What is the message? In this system, the message is the intensity of the molecule, how to say that, concentration of the molecules per unit meters to the third power.
So if there's a
Yes.
concentration that passes a certain threshold, then you're
yes. Pass a concentration has over a certain threshold, we can understand it as a bit 1 or symbol 1, and under the threshold, the concentration under the threshold, we can think of it if it's a bit 0 or symbol 0. You can like this to like a concentration encoding or some modulation techniques using this.
But in that case, because they have a fan,
Okay.
they have like a number of ones that are going to be overshoot.
Oh yes, there will be some problems like inter-symbol interference, because we first we will have to synchronize the transmitter and receiver, and say we have time slots and agree with the transmitter and receiver, and like Alice and Bob agree with some time slots. And for the first time slot, we will detect the threshold, whether the concentration is over the threshold or under the threshold. And some bad news will say the former time slot will have some interference about it later. So that is the challenges to conquer in this field. Yes, but if the time slot you can make the time slot very long, so that the inter-symbol interference is not very severe. So they just want to demo, and this can be realized in the tabletop system, but not to optimize this system. It's just,
And like last question is, you mentioned communication on like a real system, like between bacteria, for example.
yeah, bacteria. Yeah.
Do we know about like this information threshold for the bacteria? Like how much
There are some practitioners working on molecular computation. Some practitioners will collect the data and to match the theoretical and practical. That can be done, and some people is doing that. Some people are doing that. Yes.
So we probably try to model something similar.
Yes, we try to first mimic and understand, and then make some man-made system to mimic those scenario between the bacteria. Yes, that's one of the purpose of the molecular communication research. Okay, thanks for the question.
Could you describe more about the experiment?
The experiment. Oh,
yeah. Could you,
yes.
The bacteria.
Bacteria. Oh, this is not the bacterial one.
Oh yeah, but where's the
this is the transmitter, and it will emit some alcohol molecules,
okay.
And the molecules will diffuse onto this receiver, and receiver will detect per each inside each time slot how many molecules comes in, and will make a threshold to over the threshold and under the threshold to represent bit 0 and 1. Yes. So there's another news. the 6G communication system, not only the molecular communications, the 6G protocols will be there will be a physical layer called biophysical layer. This is a very rather new concept. Biophysical layer will include this molecular communication into their will hopefully include this molecular communication into their standard. And just a coming workshop called 6G Live. There's a topic related to molecular communications. And notice that the two organizers are some experts in the quantum communication, because they post very rich paper about entanglement assist communication systems, because they think the 6G in the 6G stage, entanglement will be a resource, and also molecular communication will be another way to realize 6G. So the same organizers from quantum society will organize this molecular communication. And this is side information. Okay, and so okay, let's go into the second section. The second section is roughly about how to mathematically model the diffusion effect. I will say this in a very brief introductive way. The diffusion can be modeled as a random trajectory if you focus on a single message molecule. So perhaps the simpler way to say that is a random walk, and a more detailed version is the Ito diffusion process. We can view these are two terms. The second term is about the Brownian motion, and the first term is about a drift. So you can think of this as a deterministic part. The first part is a deterministic part, and the second part is a random part. And you add these two terms up to get an infinitesimal shift of the per simple base molecule. So this is the mathematical modeling of the random trajectory inside a MC system. Also, another viewpoint, and rather most of the researchers in MC field will adapt this, because this viewpoint is more similar to the traditional EM wave communication systems, because they can draw into the block diagrams. Maybe you are familiar with these block diagrams. And roughly speaking, if the messages is encoded in the concentration per space, this is a transmitter and this is the bulb side, this is the receiver side. If we assume that the receiver can measure the number of molecules per space, so we can just describe this as an impulse response. What is an impulse response? It's just a function of space and time. So if we can characterize the function over the concentration of molecules over space and time, we can always get the CIR. CIR is the local concentration near the receiver end. So if we model as this, we can use the engineering mathematica, in engineering mathematics textbook as a important technique is a partial differential equations, and partial differential equations can capture the evolution of the concentration over the space and time. Yes. So okay, so we can use the macroscopic viewpoint and transfer our problem into a PDE model. The PDE model stands for the evolution of this concentration of molecules. So that can capture all the evolutions. And perhaps in this viewpoint, the hard part is to solve this equation. For the simple case, it is solved in 19th century, and the solution is denoted by C star. So C star is a function that satisfies this partial differential equation model. So let me abbreviate. A partial differential equation use PDE to abbreviate this. Okay, So this is a plot of the concentration. If we fix the location and measure the concentration evolution over time, if we fix the receiver location and measure the concentration over time, so this is the plot. So maybe this is one symbol, and you can say you can set a threshold here and to seek whether the peak concentration is over the threshold or under the threshold to decode the bit 1 or 0. That is the main concept. And for the further case, we always want to add a drift because pure diffusion is not very efficient in transferring these molecules to the other end, because diffusion is zero mean in position. So we in many applications we want to add a advection. Advection is some equivalent roughly to the drift. So if we add a drift, there are two main consequences. The first consequence is the molecules in average go to the receiver end more quickly. That is the first advantage of adding a drift. And the second advantage of adding a drift is they goes kind of like more concentrate between each other. So this is the drift effect. But the drift effect, if we want to add a drift effect, the diffusion equation will change and will be more complicated. So the challenge here is reduces to how to solve this concentration over any space at any time for more complicated equations. So that's one of the many of the research might follow this philosophy. Okay, so let's go to the other philosophy or other paradigm. That is a channel called a first arrival position channel. This is our main topic. So we end of the introduction part, and we will go to the main result from this page on this slide. Okay, so let me introduce the related the system model of our research. So this is another molecular communication systems, and I put the information source at the right-hand side. So you can think of this is Alice, and the information sink is Bob, or equivalently, this is the transmitter plane, and this is the receiver plane. What is the reason to use a plane? Because we want to record the emitting position vector and compare it to the received position vector. So maybe this is a more precise figure. Let me discuss this figure in more detail. This is all the things I will consider. So there's a man-made transmitter plane, and another man-made receiver device is put it in red. And if we choose a position in the transmitter plane, there's a two-dimensional position information embedded in this molecule. So the information is embedded in the transmitter plane. There's a two-dimensional location, but the lambda has no information because lambda is the prescribed distance between the LSF bar. So let me embed the position information in the first two dimensions and let each molecules to diffuse and hit the receiver plane. And we allow an arbitrary vertical drift to boost this diffusion. And this is our model. And our problem is, the first problem is to solve explicitly whether we can solve explicitly the Y position bias compared to the X. So explicitly, we want to solve an additive factor that will be satisfying the X plus noise equals to Y. Whether we can solve this bias vector, two-dimensional vector. That is the first main problem. And this problem is solved just very recently, say the last year. So we can demo just the result and omit the details. So if we let the X to be a two-dimensional Euclidean vector, it represents the emitting vector. And then the the molecule hit the receiver plane, and this position has a bias. And the bias term can be calculated, can be modeled as the initial position add up a noise factor. And Y is the final landing or hitting position. So this can be calculated. Although it is complicated, but it can be calculated. I calculate this result not using the techniques, just solving PD, because the PD is too hard to solve. So the main technique I use to find the explicit form is to bypass or to transfer the PD model back into the Ito diffusion and use the stochastic calculus techniques, and then use the back generator to link these two. So I will suppress the detail and just show the result. The result is looks like this. And so this is a noise distribution concerning the bias of the information position. Okay, so based on this, this is the method I use, and we can separate the main technical method into 3 steps. And these are the other researchers' methods, and our method has some benefits, so we can calculate the form in a more general setting. So first, we have some numerical simulations about. We just set up a diffusion framework and to run a MATLAB program, and we let the particles to diffuse and hit the plane. So our formula just exactly capture all the distributions of these position molecules. So this will this makes some this verify that our result is correct, and then there's another analog of our channel is called a time channel. The time channel is originated in this work. There are 3 persons, and in 2012, they proposed another related channel. They just use the time to record the information. Say we can first set up a time slot, and if a single molecule hit the receiver end earlier or later, we can separate the case of the bit 0 and 1. They just use the time information of a single particle to represent the bit 0 and 1, earlier hit or later hit. That's the concept. And based on this concept, the PDF will be directly cited from the statistical research field, because they just have an exact form. So in my opinion, they just choose this timing modulation because they know the distribution. But in our case, it is not the same, because there's no such form in the literature. So we derive this from scratch. That perhaps that's a technical contribution, because the setting they choose has a known noise distribution. But our case is have to derive the noise distribution from scratch. Okay, so that is the noise distribution part. Okay, so if no questions, I will move on to the capacity bounds part. So for the capacity bounds part, I will first introduce the FAT channel. What is FAT? It is the first arrival time. So mainly, I will make the FAT equivalent to this AIGN. AIGN is some early hit and later hit case. So it is on the hitting time. So let me just introduce some known result at the current stage. So the question is that we are always very interested. We are always interested in the Shannon capacity problem of any kind of mathematical explicitly formula channels, and consider an additive channel. Additive I put in a parentheses, because this is not a necessary condition. But our case is additive. So for a general channel, the mutual information between two random variables can be expressed as this, and the channel capacity is just can be, through some coding theory, can be formulated into the maxima or suprema value of this. input output of the mutual information between the input output random variable, and the connection between the input output random variable is what I just said, noise, because there's a noise. A noise distribution will determine the transformation of these input output random variables. So because we have a new kind of noise, so we ask the question, what is the channel capacity of that new kind of noise? So this is the question. And for a comparison between the FAT, because FAT has no result, so the natural idea is to follow first the results. What is the result about FAT? So I will use some slides to explain the FAT result concerning this channel capacity. So at first thing, you can think of we have to constrain this input distribution. Otherwise, this will be infinity, because this is an unconstrained optimization problem. So we have to set some constraints on the input, and these constraints must capture some of the molecular computation concept. So that's the first problem. What is capacity of FAT, FFP? So let me see the next slide. Let us see the next slide. So the capacity of the AIGN is what we call the FAT, first arrival time channel. So the first result is about setting a average constraint. What is the average constraint physically means? What is the physical meaning of this average constraint? Average constraint is, let me use this figure to explain. We can just without loss of generality, because we are just focused on the memoryless channel case. So we can put ourselves in just one time slot. In this single time slot, this molecule will hit the receiver earlier or later. So you can imagine there's a shorter time to hit or longer time to hit. Okay. So if we constrain the expectation of this time, so you can think of the mean of the shorter time and the longer time will not be very long. So this constraint just say that you cannot spend too much to transmit one signal. So this is a physical meaning of this constraint. And the next problem and the next challenge is once we have set up this constraint, how to solve this suprema or maxima problems. So this will be attained. So I just write the next. So this work is done by this group listed here in 2012. So under the mean constraint, the capacity, the optimization value of this optimization problem can be bounded above and below by this two explicit form. Although this explicit form is very complicated, it can be written down. So this is the main result from the authors, from effort these authors. And notice that the K is the Basel function. So we will encounter many Basel functions and their partial derivative to bound this case. Okay, so that is the non-result before we have done this work. So this is the FAT result. So the problem is I was thinking about if they have a noise distribution and they can just bound upper bound and lower bound the capacity, whether we can do similar things or the analog in the position channels. But at first glance, it will be much harder because our distribution is more complicated. And we have three velocity degree of freedoms. But for the time channel, they just have one dimensional velocity. So not only the dimensional velocity will be increased to 3, and the formula will also be more complicated. Okay, so let me show what we have done. So okay. Okay. The one before.
Yeah. Okay. So the finite capacity is going to be the maximum of the mutual information that you have there.
Yeah.
And then you said on the last point that the intuitive meaning of these constraints that you cannot spend too much time to transmit one symbol.
Yeah.
I wonder why. Why is it the case?
Okay.
Is it? I think I missed something.
Okay. So there are two kind of channels I was talking about.
Yeah.
The first kind is a position channel. Position channel is more maybe more intuitive or more direct. We put the position, we put the information into the first two coordinates of the emission position, and then diffuse and will receive. The receiver will receive the first two dimensions with a bias, with a position bias. So this is the we can estimate the emission position using the random variable y. We can estimate this, so there are information inside. Oh, for the other groups, they are considered the timing channel. Perhaps the figure is not too clear. I will explain more. So they just say we are considering just one single transmission, just one time slot. This particle will be released at time 0 or time 1, say 1 second after, and then release. So the receiver and the transmitter have a synchronization of all the time. So receiver knows which when the particles is received, and he will estimate.
The receiver knows.
Okay.
The particle was transmitted.
The transmitter will know the heating time, but he will try to reconstruct the heating time to guess that whether Alice put the emission earlier or later.
Okay. So, wait. He's going to know the heating time. So he's going to know when the particle was released.
Yeah. Let me say.
And try to guess when the particle.
Guess. Like again. Let me say again. They have the same time. Two class. They own two class, and that is synchronized. So the receiver know beforehand that Alice will emit a particle at time 0 or 1, and he said after receiving the particle, say 2.5 seconds after, he must make a guess whether he released the particle at time 0 or 1. Yeah.
So if it takes too much time, it's
yes, too much time, and it's more likely to you put it late.
Okay.
Yes. So is it make sense now?
Yes.
Okay. Thanks. So this kind of channel, their bounds is first calculated. Not first. Before our work, they calculate the bounds. So I just saw these complicated equations. I want to solve our channels capacity problems and try to recover the result in the position channel. So that is our motivation. Okay, so I will omit the details. If necessary, I will show up the original papers. Okay, so these are just the results and not the details. So the first to approach the problems. So let me just say the final conclusion is we have a similar result of this. The final thing is that we just derive the upper bound and lower bound. But these are the intermediate steps, the steps between. So the first thing we just want to write down a position channel formulation. It is just a d-dimensional vector addition channel. And then we assume that our information is independent. This perpendicular represents independent to the noise. That's kind of a reasonable assumptions in communication field. So, and the next thing is the noise follow VD/FFP. What is VD? Because the case is too complicated to solve, so we just keep the only component to boost the diffusion, and we omit and we just simplify our case to not allowing the parallel drift. So we just try to derive the vertical drift case to solve this capacity problem. So that's a assumption to simplify the problem. So for the vertical drift part, this mu is a normalized drift. Because we use V to represent drift. U is the normalized drift. Normalized by what? By the standard deviation. Because in each diffusion you have a standard deviation of the Brownian motion part, so it can be it can be think of as the strength of the diffusion, and the drift will be normalized by this, say divided by the sigma. So U is the drift that is normalized by sigma. Okay, so this is the drift, and lambda is the distance between Alice and Bob. Okay, so these are two positive parameters, and we can after a long derivation, we can extend the three-dimensional case into any dimensional case. That's a rather complicated result, complicated calculation, but not very complicated in concept. So we have a d-dimensional using the Bessel function representation of this any dimensional drift, and this is the noise distribution. This is the first result. In the second result, we try to transform this into the Fourier transform. Because Fourier transform will have more nicer properties about this additive structure. Because if you add two random variables, the PDF behind will do convolution. So the convolution is not easy to calculate. So we transform there into the frequency domain, say the Fourier transform. So we try to get these into the Fourier transform. Surprisingly, the Fourier transform is much simpler than this. These are two equivalent viewpoint under the link of a Fourier transform pair. So after we get the characteristic function, we will get the moments directly, because we can do some partial derivatives and make some terms into zero to get any moments. Because a characteristic function CF, roughly speaking, is just all the moments, roughly speaking. So we will get the moments, and we will say that this is the zero mean. We can see, because we get one first moment and second moment, we can prove that it's zero mean. And then it's a very specific property used to bound the capacity. This is called the weak stability, and this is we think these are new even in the mathematical physics, because this is a new kind of noise distributions, and I want them to have a stability property. Oh, the story is that the stability used to describe some kind of closeness under the addition of two random variables. Let me say again. Say you have a Gaussian random variable and another independent Gaussian. We add these Gaussian random variables up. We will get a Gaussian. This is called the closeness property for the addition of two Gaussian variables. Whether our new noise distribution has some closeness property, and to speak it precisely, these closeness are called stability. So stability is just the two random variables drawn from the same distribution will add up back into the same family. So this is called the stability, but it's kind of weak because we have to fix the first parameter, and just the stability just happens in the second. So we just add a weak to distinguish the full stability. So this is a kind of hard work because all the hard work is reduces to the Fourier transform pair. So after we get the Fourier transform, this will be somehow direct forward from the CF formula. So we can prove this and the rules and all the rules between the parameters. Okay, so let's get into the capacity problem. So this is the capacity problem, and we choose the energy constraint. This energy constraint is to mimic the Gaussian case, because in the information theory, parallel Gaussian channels are very well-known result. And parallel Gaussian channels often use the constraint using like this second moment constraint. Just like you draw a circle and you constrain your input vector not to go beyond this unit crossbar. So it's just a unit crossbar in a transmitter plane. Oh, go ahead. So we try to use this constraint so that the result will be more interpretable. So we just use the second moment constraint. And let me just put HD to represent the differential entropy of this new kind of VDFAP. So we just have a notation HD. Okay, so using this notation HD, the lower bound can be solved because we have a stability property at hand, and we also know the, let me see that. Let me say something about this. This equality is based on the additive structure. So if we are considering the additive channel, the mutual inversion can be reduced to the difference between two differential entropy. This is because of the additive structure. And we have this structure. So we just have to calculate the difference between two H. And we also know the H because we have done a hot calculation. This is just a brute force calculation, and we can solve this calculation in two-dimensional in explicit form. So we have H2. H2 represented to the 3D channel that we are more realistic. Although we have any dimensional noise distribution, the realistic physical system is the three-dimensional. And notice that the three-dimensional system, we have a two-dimensional information of the position. So H2, we kind of lucky that we get a closed form of H2. So using the exponential integral function, spatial function from physics, and then the final part is to evaluate this difference. How to evaluate this difference? The first is the lower bound. Lower bound, we use the stability so that the n is fixed to the n is a known VDFAP, and we just choose the x to same family of VDFAP using different parameters. And we also let the parameters, the chosen of the parameters, so that the energy gets its maxima constraint value. So this is a good lower bound, a best lower bound under this constraint. Using this method, using this stability method. So using the stability method, we can get a lower bound. That's the main idea. And for the upper bound, we just use another property from information theory that property is called the entropy maximizing function. Because for each mathematical constraint, not for each, for common mathematical constraint, we have known that certain distribution will attain the maxima entropy. Say, if we constrain our variance over all the distributions with the same variance, we know that Gaussian has the maxima entropy. The intuitive is that Gaussian is the most chaos distribution under based on the same variance, because we can have a same variance and the Poisson distribution compared to the Gaussian, and Gaussian has a more chaos differential entropy. So this is a mathematical result, and there's a table of this. So when we choose the second moment constraint, we know that Gaussian is the best. It has the maxima H. So we just can bounded our capacity using a Gaussian distribution at output. So how to get a Gaussian at output, we just not know, but Gaussian will always be an upper bound. That's a statement. So we can transfer our input parameter constraint into the output. This is based on just a brute force calculation of the 4 terms, and the middle 2 terms will vanish because the zero mean of our channel. And the zero mean is based on this calculation. So we can just move our constraint in the output over to the output constraint, and then using the Gaussian maximization entropy property to get the upper bound. So that's the whole story. And the final thing is that our bound has to use the HD for the bound. And if we cannot estimate HD, calculate it explicitly bound is just a formal bound, not a explicit bound. So we try to calculate the most common case is H2, and we have this calculation explicitly done. Okay. So the last but not least, we also have to verify this difference is strictly positive. Otherwise, our capacity will be 0 and no information can be transmitted reliably. So we have do an argument to argue that this term will be strictly positive. How to argue that? First, we know that PUD lambda are strictly positive. So the problem reduces to argue that HD is monotonical, strictly monotone. So if we can argue that HD is strictly monotone, we can argue that in our story, whether if we have a positive drift, always a positive achievable rate using this kind of channel. So that's kind of interesting interpretation. So the last thing we just try to prove that this is a strictly increasing function, and we can do this. We can do this. So the conclusion is that H2 is also strictly increasing. So saying that our channel will have a positive achievable rate. So that's the whole story. And the final thing, we plot this over these different parameters to show the gap between upper bound and lower bound to see whether our result is good or bad. Kind of good, because the first, there are 3 figures I want to explain, and then a conclusion. The first figure is plotting the capacity over parameter P. What is P? P is, say, the input constraint. How spread can the input distribution be? How diverse? So if you let the randomness of the input to increase, so the capacity increases, and our upper bound and lower bound will go into the same direction, and the gap is not too large. So let me fix the other 2 parameters and plot between lambda. What is lambda? Lambda is the distance between Alice and Bob. This is kind of makes sense, because if you put Alice and Bob far away, that is, the lambda increases, the capacity will go down. So that's kind of intuitive. And the final thing is about the drift, background drift. If you add the drift, increase the drift, the capacity will increase. The right part of this line tells us the story that if we have a drift to boost this diffusion, the capacity will increase. But interestingly, the bound kind of fails when the drift approaches 0. So this becomes another open problem we are going to solve, or someone will have an interest, can have a look over this. So this is another open problem we haven't solved in this current version. So just go to the conclusion part. So let me first recap some of the key points. The first point, take-home message, is the noise distribution is recently derived, just last year, based from our group. So based on the noise distribution, we are curious about channel capacity, because the most simpler channel capacity is for the memoryless setting. So it is a direct question can be asked. So the capacity bounds for the analog part, the FAT channels, was studied by these 2 groups, 12 and 14. And we try to solve the FAT channel analog, say the FAP upper bound and lower bounds, by our group. So this is the recent result, and we just have the upper bound and lower bound. But there are some open problems. One of the open problems is that when the drift approaches 0, all these analysis fails down. So this is a kind of interesting property, and if we can make some explanations, it's also good. So the second one is because all we consider is the point-to-point setting, and also the memory the setting. So if we go beyond this setting, we can do something like multiple access channel, say 2 eddies will access the same position channel, how the capacity region goes. So that is the 2 interesting open problems need to be solved. So I think the time is exactly the 11. So the last slide is about the question part. So thanks for your attention. If you have any question, you can ask. Thanks. And by the way, I'm the speaker, and this is my email. Okay.
Yeah, thank you for the presentation. So, as the speaker said, does the audience have any questions?
So the extensions, 2 interesting extensions. This, I think that is what I'm going to. I'm very curious about these 2 questions.
I mean, I have a question. It doesn't seem to be the case, but I do wonder if there's anything on like the quantum realm that kind of compares to this.
You are saying about is there a quantum analog comparable?
Yeah, or something like this, because when you're thinking about this information that you're sending between transmitter and receiver, you're talking about molecules, right?
Yeah.
Is there like any quantum effect or anything that would
that's a good question. Actually, I was thinking about this kind of modeling, but it's kind of a modeling at the stage of the modeling problem, because in the field of molecular communications, there are still no quantum effect. They are the scenario they are considered. So maybe some of the possibilities, where say we can have an entanglement between the Alice and Bob. Say we can have entanglement between the molecules each other. Say we can have molecules to entanglement with the Alice or Bob. So that's kind of interesting questions to ask, but they're still at a very early stage. So if we can propose the first meaningful analysis of this kind of story, it would be good. It would be good.
All right, thank you.
Thanks.
I think we don't have any more questions, so let us all take our seat.
Thanks. Bye-bye.
And let me stop the recording.